This video is for graphing for slope, but it is also for circular motion because it does both. And it starts with taking a disk and it spins around in a circle. That's the circular part. And we know that if it's circular, we know we're going to have to do sigma f equals mv squared over r. We can sort of start with that. That's how we know it's a circular thing. It's moving in a circle, and we know some force has to be that. Also, through the course of this, we're going to graph something and use the slope to find the answer, and so it actually takes care of two of them, and so that's nice. It also is one of the ones that uses variables, and it's probably one of the harder algebra ones with variables, so get ready. We have an experiment before with the apparatus above. This is an apparatus we actually did an experiment with in class. Ours was just a stopper, but we have a disk on a frictionless table going around. They did that so they could make it flat. And we put this mass on the end of there so that we know exactly what force gives us the sigma f equals mv squared over r. For this case, it's gravity, and it's going to be the m2g gravity. So we start part A with setting that equal to mv squared over r. Our goal in part A is to find the equation, derive the equation p equals 2 pi squared of m1r over m2g. And so that means we've got to have a series of steps and come up with that. And so that's a little more abstract than most problems are. And we're going to start it, though, the way we always start circular problems. We start with this and we set m2 equal to that. And I'm going to kind of work it over the side because we need a little more space. So what I say is that m2g equals m1, which is the thing going around, v squared, and a little r, because that's what the radius is right there. And I know that that's a good place to start because I know that that's true. It has a bunch of the variables I need, m1, m2, v, r, but it doesn't have period in there. So I need to find a way to put period in. And the way that I put period in this case is that I know that the velocity is distance over time. And for a circle, the easiest distance and time to find is the circumference, 2 pi r over the period. So I'm going to plug that in for the velocity here. And so I get m2g equals m1. And for v, I put 2 pi r over period. Make sure I square all those over r. Okay? And so when I square all those, I get something pretty complicated. I'm still going to have my m2g over here, although I'm going to add the r over there to make it a little easier to write. So my r is over there now too. Over on this side, I have m1. I have 4 pi squared r squared all over r. No, I don't want to move my r. I'm going to leave my r over there because I'm going to cancel one of them. So that r cancels with one of these r's there. And I'm going to move down to here. And I'm going to say, oh, I have a p squared that I forgot about. P squared right there. Take my p squared to the other side. That's what I want to move to the other side. And I get p squared m2g equals m1 4 pi squared r. When I get p squared by itself, so then I can square root everything. So I say p squared equals m1 4 pi squared r for m2g. And I square root both sides, giving me exactly what I wanted. And the 4 pi squared comes out because when I square it, it's 2 pi. So p equals, I'm going to square root that side, square root this side, 2 pi times the square root of m1r divided by m2g, and that's exactly what I wanted, so I'm finished with part A. That is a really hard part A. Because of that, it has a lot of partial credit. But we can do this now. Make sure you know how to do this. I kind of backed down after this one and made a lot of easier ones to come from, but you always have to derive it in this kind of graphing for slope problem. So you're always going to set two things equal. A lot of times it's forces, sometimes it's energies, but you set them equal and solve for certain things. And then they always give you some kind of a data table. And these are the two things that they changed in this particular experiment. They changed the mass too, and they saw how that affected the period. And they're giving you some numbers here to make things a little easier for you. And we're going to go ahead and figure out what qualities give us a straight line graph where the slope can be used to determine g. And so I want P and M2 need to be the two things that become my X and my Y, because that's what I can graph. And so I want to make this so that I have M2 and I have G on different sides. And so the one I like to start with is this one right here. I don't want this one here because I have a bunch of weird squares in there and I don't really like that. So I'm going to start with this one here and find something that I can use for my y equals mx plus b. I have p squared m2g equals m1 4 pi squared r. I want to get the m2 to the other side because I want to say y equals mx plus b, and I want to get the g to the other side because I want the p to be by itself to be my y. So I end up with p squared equals, I want my m2 to be by itself, and then other than that I have m1 4 pi squared r over g. I'm going to switch those because I want y equals mx plus b, and I get p squared equals m1 4 pi squared r over g times 1 over m2. So basically I want to get it so that everything except for the m2 is in front of the m2 so that I can say this is y equals mx plus b. So what I want to graph, which is what b is actually asking, is I want to graph p squared versus 1 over m2. If I graph that, I'll get a straight line and my slope will be something with g in it, and I can solve for g. All right, so that's what I'm going to do. To do that, I have to find 1 over m2 and p squared. And so I put all those things in my calculator. 1 over 0.2 is 50. I get 25, 16.6, and 12.5. When I square 1.4, I get 1.96, 1.06, 0.64, 0.56. Then I flip over to the next page, and I want to graph those. When I graph things, I always need to label my things. My y was p squared, my x was 1 over m2. I put my units, 1 over kilograms, because it was a mass. Over here, seconds squared. My units, I know that my p2 goes up to 2, and so I look to see, and that's about 2, 1, that's good. This goes up to 50, so I'm going to go 10, 20, 30, 40, 50. Then I start graphing my points. I have, for my x is 12.5 and then 0.56. So I go to 12, 10, 11, 12.6, somewhere around here. Then I go to 16 and 6. So I go 15, 16, and about 6.4, right there. I go to 25 and 1, so 25 and about 1, 50 and 2, 50 and 2. So those are my numbers. You would use a straight edge here, but you want to get as close to a straight line as possible. But they don't have to go through any of the points necessarily. And you pick, and you pick 2 points on your line because you always find the slope of this thing. And so that's a good point where it crosses, and that's a good point. You do not want to use the actual points that you used to draw the line. They always look for that. Using my graph to calculate the value, which is my last part, I just find the slope of that. And the slope, again, equals rise over run. And for this, it was about 0.039. And from my equation, I know that that 0.039 has to equal m times 4 pi squared r over g, because that's what my slope was right down there. So I set that equal to m1 4 pi squared r over g. I know everything but g, so I set 0.039 equals 0.012 times 4 times pi squared times 0.8 all over g, and I got my g value to be 9.7 meters per second squared, which is pretty good. It's supposed to be 9.8. Don't forget to label your axes and label your scales, because on these, a lot of times they give you a lot of partial credit on them. Don't use the points when you find the slope. You know, the hardest part is actually deriving what you're going to graph versus what. So be careful in your derivations. Set things equal to each other. Make sure you know how to put into y equals mx plus b format. And that's about it for this problem.